Alright, so we're finally sort of ready to start analyzing three-dimensional statics problems. So in this case, what we have is a very simple kind of structure. We have something that looks like a handle, but it's obviously quite long. We have 2 meters going this way and then 1 meter going this way. And there's an external force applied at this end, and it is expressed in terms of its vector components. So now we're going to be using vector analysis to basically analyze this system in terms of its reaction forces. So the idea is, given that this handle is essentially fixed to the wall, we want to find out what the reaction forces are going to be at the wall. So we want to know exactly what forces are involved here so that we can design this thing to actually withstand that kind of force. So as we always do, what we're going to do is we're going to draw the Freebody diagram. So we're going to draw the handle here. And it is going to look a little bit like this. So we know that at the wall, because it's a fixed kind of support, we're going to have the following. We're going to have some sort of force, some reaction force in the Z direction. So let's call it RZ. Then we're going to have some force in the X direction going this way, and we'll call it Rx. And then some force in the Y direction, and let's assume that it's going this way, so let's call it Ry. So we have 3 reaction forces, each one in each of those coordinate axes. And then notice that because this is a fixed wall, we're also going to have a moment reaction. But that one is going to be a little bit tricky because we need to know exactly about which axis this thing is rotating. And the first thing we notice is, well, this is actually rotating about the y-axis. So we can assume that the moment is going to be about the y-axis. So let's call it my. Normally, we would have moment reactions about all the axes, but in essence, in this case, the main moment is going to be at the y-axis. But let's just try and do all the moment reactions just for the sake of argument. So, because this thing is pulling this way, we can expect that there will also be some moment reaction along the x-axis. So, let's say we have a moment reaction here. And now we have a moment reaction in the Z direction. So, let's see what that is. So if this one is pulling this way, this is causing it the rotation this way. So the moment reaction here should go like that. So it gets a little bit messy, but hopefully this will all make sense once we derive the equations of equilibrium. And then we have a force here, or force factor, which has these components. And of course we have the distances here because we're going to need those to calculate the moment. So we have 2 meters. And then we have 1 meter here. And obviously this is a right angle, so just to point that out, that's a right angle there. Okay, so let's write down our equations of equilibrium. So the first thing we're going to do is we're going to do sum of the forces, and now we do it as a vector, has to be equal to 0. Well, that's not very useful, so we need to break this down into different components. So we're going to have sum of the forces in the x direction need to be equal to 0, and we're going to assume that this is the positive direction. So let's have a look at what we have here. Our free body diagram is telling us that we're going to have a moment reaction. Actually, this is going to go inwards like that. So this force is coming out. It has an x component that is actually being projected like this. So we're going to have the following. We're going to have Rx minus 3. So that implies that Rx has to be equal to 3 newtons, because this is essentially the x component of that force. Then sum of the forces about in the y direction. Well, the y direction, we're going to say, well, let's say that this is the positive orientation. So we have minus Ry. And then this one has 2 units along the y direction, so we're going to have plus 2, which implies that Ry equals to 2 newtons. And finally, the sum of the forces in the Z direction, assuming this is the positive direction, we are going to have the force here R set, so reaction set, minus this component, so basically that's going to be going downwards, so minus 2, and then we have R set equals to 2 newtons. So that seems reasonable enough. Now what's going to happen is we're going to have our it all balances out in the end, so what we need to find out are the moment reactions now. But if we wanted to write down the F, basically the moment reaction or the force reaction in terms of a vector, what we would do is we would write something like this, and then we would write the components. But now we need to take into account the direction. So we said that this one was going like that, this one is going like that, and this one is going like that. So if we look at the orientation of our axis here, we know that this direction implies this is going to go in the negative x-axis, so that's minus 3. Then this one is going to the left, that's minus 2. And then this one is going to go up, so that means that's going to be 2. And it makes sense because we would expect the forces to basically have the opposite sign to these ones. Now for the moments, we're going to do the same thing. We're going to grab some of the moments about some point O, and moment is going to be a vector quantity, but once again we're going to break it down into 3 separate equations. So we're going to have some of the moments in the x direction, or basically about the x-axis. So what are we going to have? Well, we're going to have this moment in this direction, so let's assume the direction is like this. That's a positive, so we're gonna have moment x, and just not to confuse it, let's put that in brackets. And then we're gonna have a moment generated basically by the force acting about, causing a rotation about the x-axis here. So that force is actually going to be the z component of that. So the z component, which is going to look something like that, is going to cause a rotation about the x-axis. So we have 2 meters, that's the distance, and the z component here, so that's going to be minus 2 times 2. So that implies that mx is going to be 4 newtons times meters. So those are the units for moments, newtons times meters, just the same units as torque. And the reason for that is that we have this moment going in the opposite direction. This here, this is causing a rotation in this direction. So basically we just make this moment equal to that. So that's how we have it here. Now for the next one, we're going to have some of the moments in the y direction must be equal to 0. And then what we're going to do is we're going to grab this. So let's assume that this direction is positive. So now we have this direction as positive. And we're going to have my. And let's see which of these force components is actually causing a moment about the y-axis. Well, it turns out that x is not really causing it because that's not related to this rotation. What we do have though is we have not the z component rather, but the y component itself is not really causing any trouble. So yeah, that's not really what we have here either. So what we're going to do is we need to really look into what is causing the rotation here. So the z component, so it causes a rotation about x, and it also causes a rotation about y in this case. So that's really important. So the z component, this one here, is going to cause a rotation about there. So basically you can imagine that you're pulling down on this, and then this thing is going to tend to rotate in this way about that point. So this component is going to be included. And basically we notice that this is actually causing the rotation in the same direction. So that means that our assumed direction for my was wrong. And then we're going to have minus, or let's say plus, something like we have 1 meter times the set component, so that's 1 times 2. Therefore, my is going to be equal to 2 newtons per meter. But now this is actually going to go in that direction, because we know that it doesn't make sense to have it going in the same direction. It wouldn't really be a reaction moment. And finally, we're going to have the sum of the moments about the z direction. So we're going to go back here, and now what we're going to have is this. So what force component of this force is causing a rotation about the z-axis? Well, the x component, if we draw it here, is actually causing a rotation about the z-axis. So it makes sense to have the moment reaction having here, and then the distance is just going to be the 2 meters going along. So x component. So let's assume that this is the positive direction, such that we have mz minus 2 times 3. Therefore, mz is going to be equal to 6 newtons meters. And we know this is the direction of that. So that's it. We just found all the moment reactions, all the force reactions, just from a 3-dimensional problem. Notice that this one was relatively easy because there was only one force involved. Obviously, there are many cases in which things can get a lot more complicated, but we haven't really done anything new here. We have just used the same concept from statics and equilibrium equations to find the answer to this problem. So this is a really, really nice example of how you can use those concepts to basically solve for all those 6 reactions at that support.